Hello, family. It's Kusekwa again. Going for heat transfer. Previously, we started about the thermometry. We said heat has three parts, and we have the thermometry, heat transfer, and the thermodynamics. So you make sure if you haven't studied about the thermometry, don't come here. Go and study thermometry and then come to the heat transfer. Now we go. So talking about the heat transfer. So talking about the heat transfer. Here about heat transfer, we're just going to speak about the three things. Heat transfer is now the method by which there is a movement of heat from one position to the other, from one point to the other, regardless is within the same body or to the different body. So talking about the heat transfer, actually, here we're just going to discuss about the methods. So considering your syllabus tells you to start about the three methods, which is radiation, convection, and the conduction. So talking about actually the conduction, we are just going to start about the three basic concepts. And the first, here I'm just going to start with the conduction. So heat transfer, this is actually about what we call conduction. Here we're just going to talk about convection. And we are just going to talk about radiation, the thermal radiation. Now, about the heat transfer now. Talking about actually the heat transfer is about these three methods according to your syllabus. But talking about the conduction now, let me talk about the conduction. Is where I want to focus. The first thing is about conduction. The thermal conduction. Thermal conductions can be electrical conduction, but this is thermal conduction. So this is just the method of transfer of heat from one position to the other, but without a visible motion of particles. Chief, before you go anywhere, you need to understand the actual definition of conduction. And I underline this word that there is no visible motion of particles. That's thermal conduction. So heat is being transferred from the position to the position without a visible motion of particles. You don't see the motion of particles, but there is a motion of particles. And before you go anywhere here in conduction, you just need to understand about the basic concepts, the four basic concepts about conduction. First thing, you need to know what is insulator and what is conductor. You need to know about the lagged and unlagged material. You need to know about the mechanism of conduction, Chief. And finally, you need to know the uses of conduction, thermal conduction, how the knowledge of thermal conduction has helped you. You need to know about those concepts. If you know about that, now I'm happy to move you to the other two concepts. So here we're just going to talk on conduction. We're just going to talk about actually the Fourier's law, the basic concepts, and I'm going to do about the radial lines of heat flow. Are you there? Let's move on. So let's talk about the thermal conduction. So talking about the thermal conduction here, I've just said I'm just going to discuss with you about what we say is the basic concepts. Note them down before you move anywhere. Concepts. We just go to discuss about what we say the Fourier's law. And finally, radial lines of heat flow. Okay, Chief, let's move on. Let's start with these basic concepts. I've just said there are 4 basic concepts that you need to understand them before you move anywhere. So talking about these concepts, I've just said about the insulators, VC conductors. You need to know. I need to confirm if you know about the first thing. The second thing that you need to know actually here, you need to know about the mechanism of conduction now. Conduction. Chief, you need to know actually what does it mean to say conduction has just a certain application. So you need to know about the uses or applications of conduction. And finally, you need to know about the lagged and unlagged material. Okay, let's discuss about these 4 terms. So talking about the insulators and conductors, actually the insulators, these are material that doesn't allow the passage of heat through them. And you need to know here, you need to know the characteristics of insulators. The question doesn't come to ask you a Form 5 student or a Form 6 student just to define. No, it just comes in conceptual term. Do you know the real features that this should be a conductor for heat? So I can tell you why copper should conduct more heat than what we say even aluminium. So they make you in comparison of different metals, and they ask you the terms in terms of application. So talking about the insulators, they have the 2 basic characteristics. The first characteristic for a conductor, the material which allows the flow of heat, but insulators doesn't allow the flow of heat. And so talking about the basic characteristics for conductors and insulators, so the reverse of this is the reality of this. So talking about the conductors, they need to have the ability to sense the presence of temperature. What this ability? This ability is measured by the specific heat capacity. What is specific heat capacity? The heat required to rise a K, 1 Kelvin for a 1 kilogram. Change in temperature. So it's the heat required to rise the temperature of 1 kilogram here. So heat over the change in temperature. So if you put a small amount of heat and there is a rising temperature, that's chief, we say there is a low specific heat capacity. But if you put very large heat and then there is a small change in temperature, that's not good conductor, meaning it have the high specific heat capacity. So for a conductor, we need to have very low specific heat capacity. But here we need to have a very large specific heat capacity high. Why? Because for a conductor, we just need a small heat to rise its temperature. Let's go for the mechanism now. Talking about actually the mechanism. Also, you need to know there are 2 characteristics I've just said about the specific heat capacity and about the conductivity. If the thermal conductivity, even if it have the low specific heat capacity and it have a very small thermal conductivity capacity, thermal coefficient of conductivity, that's not a good conductor. So to be a good and more efficient conductor needs to have the 2 characteristics. One, low specific heat capacity, and the second is about the thermal conductivity should be high. So characteristics of insulator. I've just started now to move. I've just started. Hey, where is my duster? Dang, it's here. Yes, just move on. We have started about the thermal conduction. So talking about actually what we say the characteristics, basic characteristics of conductor and insulator of conductor. So you just revise them. First thing, it should have the low specific heat capacity. And the second thing that you need to know, it have talking about the insulator, it have the high, no, the conductor high. We say thermal coefficient of conductivity is K. We learn in Fourier's law. Worry not. So moving on, let's go on for the second concept, which is now the mechanism for conduction. Actually, heat is being conducted from one point to another without visible motion of particles, but there is motion of particles. So talking about the mechanism of conduction now, it can occur in two phases or in two ways. One is by vibration of particles, and the second is by the movement of electrons. So actually, speaking about the mechanism for conduction, here we just mean let me start the first one by vibration of atoms. The region where there is high temperature, particles tend to vibrate much with high kinetic energies because the kinetic energy is directly proportional to the absolute temperature. And so when they vibrate, they tend to vibrate like phonons. What are phonons? These are just elastic particles that tend to transfer energies. So particles at the hot junction tend to vibrate at the mean position. They don't move, but they tend to vibrate at the mean position. So it's like elastic waves. As they vibrate at their mean position, they tend to induce the energies to the next particles towards the cold junction. Hey, come on. I said in thermometry, heat never flows from the cold junction to the hot junction. Always flows from the hot junction to the cold junction. And so, if we are talking now about the transfer field, the mechanism, we are now speaking about from hot junction to the cold junction. And if it occurs in reverse, we must apply the energy to reverse the path. For example, in refrigerators, we'll talk about them here in convection. But let me pause about that. So talking about the mechanism by vibration of atoms, you say at high temperatures, particles have the high kinetic energies that makes them to vibrate at their mean position, inducing their energy to the next particles toward the cold junction. That's how you have done, Chief. Talking about by movement of electrons at the high temperature region gets the kinetic energy than the cold, so they tend to move toward the cold junction. That's how metals are good conductors of heat, Chief, than any other materials. Why? Because metals tends to have the metallic bonds. Now, the metallic bonds make them to have the free delocalized electrons. And so because the electrons are so faster, tends to make them more conductive than those atoms, by those which only depend on the vibration of atoms. So we say by mechanism now by motion of electrons, we just say electrons at high temperature tends to have the high kinetic energy, and then they move toward the lower the cold junction. And since electrons are so more lighter, the conduction by the motion of electrons is more efficient than that of vibration of atoms. So Chief, talking here about the mechanism now, about mechanism. So about mechanism is by vibration of atoms and by motion of electrons. And actually, Chief, here, come on, see. Most of the questions here ask you why metals are good conductors than other materials. Some materials are conductors of heat, but they are not much efficient as metals, because metals tends to operate with these O2 mechanisms, while for all other materials which doesn't have delocalized electrons, like in metals due to metallic bond, they just uses this one. Dang, there we go, Chief. So the other concept is about the applications of. Oh, before I speak to applications, let me finish about the lagged and unlagged material. So talking actually about lagged and unlagged material, the third concept is about the lagged and unlagged material. Unlagged material. Ooh, chief, huh? This physics is sweet now. Yeah, sweet. If you understand physics, nothing is bad in this life. Everything is good. Okay, let's move on for the lagged and unlagged material. Talking actually about the lagged and unlagged material, this lagged material are just material which have been covered with insulators on their surfaces so as they not lose their heat to the surrounding, but they tend to lose their heat due to the vibrational motion of atoms or the kinetic energy of electrons. So talking about unlagged material, a material which have not been covered with the insulators. So they tend to lose directly their heat to the environment. So talking actually about the lagged material now, they tend to ask you, how does the temperature, the decrease in temperature for a given length is associated with the length? We say the temperature gradient. So if here is hot at this point, and then here is cold region. So for a lagged material, since there is no heat loss to the surrounding, there is a linear temperature gradient. The decrease in temperature for a given length is linear, tends to decrease linearly. So we speak about lagged material, their temperature here with their length. If this is the lagged material covered with the insulators here. So as the length increase, its length, this is the length, from here to the cold, and this is hot. As the heat covers the distance, we say this is the temperature and this is the length. So they tend, look here, chief, to decrease. Fine, if here is hot, having temperature theta, and here is cold, 0. So as the temperature moves from theta to the cold junction, as the length increases. So as the length increases, the temperature tends to decrease, but linearly. But talking about the unlagged material, for unlagged, which is now uncovered, material which is now uncovered like that, tends to lose heat toward the environment. So there is a loss actually, but the loss is not linear because the environment has we haven't determined actually the factors that affect the environment, the loss of heat through the environment. So actually it's not linear, it's exponentially decreasing. So this is theta and this is length here. So heat tends to move from the hot junction here, just being loose, just being loose towards the environment actually, the heat, reaching here, very small heat, chief, and the graph is not linear as again. There we go. So the fourth concept that we are going to discuss here, the fourth concept here is about the uses. Make sure you have my book. Nothing works without that book. So in that book, you just follow what I've just written there. Let's go on for the applications of thermoconduction. Talking about the application of thermoconduction, we just mean one of the application of thermoconduction. Let me write here the thermoconduction applications. Applications, chief. At home, you are using the cooking utensils, which are metals, either aluminum or any other material, iron. But what is fantastic, the handles can be plastics or any other insulators. So cooking utensils are just made of conductors but packed with the insulators. Why? Is to make sure that you are not burned when you are holding them. So we just say cooking utensils are made of what do we say? Insulators, handles which are bad insulators. Are you there, Chief? The second thing that we need to know about the what we say, the application, the other application, when it's the cold condition at a time. Actually, we wear the woolen coats which have been made by wools, the cottons. Why? Why do we wear such blankets or such jackets? The reason is within the wools, or we call the cotton, there are some fine pores. So there is air between the fine pores. Air is the bad conductor. So the heat from the body inside cannot move easily outward because there is fixed airs within the pores. So this is the bad conductor of heat. So you don't lose your body temperature toward the environment. Well, if you don't have, it's like you are unlagged. Do you remember that concept? Yeah. So talking actually about the application, one of the applications is about the woolen cloth. Woolen cloth tends to be warm. Why? Because you are not losing heat. Your heat is incubated. Okay, the third thing about the uses. Hey, how about conduction? Do you know, talking about the conduction, one of the application also of conduction, we can just say, over here, with this. Hey, oh, this is about, here we haven't finished about the Fourier's law. We'll talk about the Fourier's law just after finishing this. Oh, wow. Hey, did you know why when you put the hot liquid on a glass, it tends to make some cracks? The reason is when you pour the hot liquid on that glass, the temperature has just rise to the other side, while the other side is too cold. So the actual contraction and expansion, the rapid expansion on the other side makes the cracks. So cracks on the glass when hot fluid is poured on it. There is where we go, Chief. And so, okay, my camera is well. So to actually talking about we're talking about the glass cracks due to contraction, a rapid contraction, than the other side. But also one of the application, the fourth one of heat conduction, come here. Have you ever heard about the cold rooms? Cold rooms, these are just rooms to store some agricultural products or any specimens that needs no changes of temperature. So for example, you're transferring viazi vitamu from Iringa to Dar es Salaam. So you needed the cold rooms, the car with the cold rooms, or the planes with the cold rooms. The cold rooms are just made with very thick walls and are made of insulated materials, which cannot just lose heat easily. So the heat is just maintained inside. The coldness is just maintained inside. And so we say the cold rooms are made with thick walls. Why? It's the application of the conduction. So we say cold rooms. Cold rooms walls are thick. Thick. Why? You know now the reason, Chief. It's about to increase the gradient for the conduction. The second thing, the fifth, we just say about the carpets previously. Previously, when I was a child, at our home, at night, the floor was so cold, and so my dad bought a certain material called a carpet, very smooth. So as during the nights we don't feel cold touching the floors as we walk. So the carpets actually are made due to the knowledge of thermal conduction. So the carpets, since are insulators, doesn't conduct easily your heat from your heat from your feet to the ground. So we say the carpets carpets on the floor feels hot or warm than the floor. The concrete floor tends to feel cold during the cold. Why? It's because if you have the concrete floor, it tends to be the good conductor of heat away from your feet. The fifth thing, too many applications. Let's see end there. Double glazed window. Double glazed window. Actually, these are windows. Do you know? It's not like here in Dar es Salaam. In Dar es Salaam, we just have the windows which have only one pane, a glass. But talking about, for example, in countries, no, it's not even in outside countries. Okay, just say even at Mbeya, the Northern Highlands, Mbeya, Iringa, Makambako, Makambako, for example. Talking about Makambako, actually, it's so cold. So, in order to protect human beings, we maintain our body temperature. So we just use the double glazed windows. Windows are made of the two glasses. So there is one glass and the other glass, and here inside there is a hair. Here is the bad conductor of heat. Glasses are bad conductors of heat. They are insulators because of high specific heat capacity and the low thermal conductivity. So do you remember the criteria for that's very important, Chief, before you go anywhere. So talking about actually the double glazed window. So when they ask you double glazed window, what are they? These are windows with the two glasses and air between the glasses. Those are just application of thermal conduction. Done with the conduction. Let's go for the second method. Second method is about no. We haven't finished. This is the first concept, just the basic concepts that you need to know about the conduction. So let's go about the Fourier's law. The Fourier's law is the law that explains actually about the thermal conduction. Let's discuss about the Fourier's law. Fourier's law. No. So how about the Fourier's law actually? Talking about the Fourier's law, this is the law that explains the conduction. And it says the rate of heat conduction, this means the heat flowing per time, is directly proportional to the area of the conductor and the temperature gradient. This means if I have this is my conductor, having cross-section area A and having the length X. So if I took this is hot junction Q2 and this is Q1. So this is hot and this is cold junction. So if I measure its heat, rate of heat flow throughout the conductor should be here. If we remove the proportionality, we put the constant K. And then its area, cross-sectional area, not its area, cross-sectional area. And then we have theta, which is hot, 2 minus theta 1 over x, which is the length. There is what you need to understand before you go anywhere. But there are some technical terms here to note. I've just said about the rate of heat flow. What's the rate, man? Rate of heat flow, of heat flow. That is the heat flowing per time. What is about the thermal conductivity? This K is the thermal conductivity. Thermal conductivity. K. What is thermal conductivity? Thermal conductivity, this is now the coefficients that determine the rate of flow through the heat, the conductor. So the amount of the rate of the heat, amount of heat flowing for this conductor per given area of the conductor per given temperature gradient, what the temperature between here and about its strength. That's what we say the thermal conductivity. So it's just the rate of flow of heat for a given cross-section area of a conductor for a given temperature gradient. How about the temperature gradient? What's the temperature gradient? It's still technical now. Yeah, okay. Temperature gradient. Talking about the temperature gradient, this we say is the changes in temperature. Temperature between these points and these points. What's the temperature in between? And the length. So the ratio between the difference in temperature for a given length, that's what we say the gradient achieve. So talking about the gradient actually is the changes in temperature for a given length. But this is the cross-section area. Let's discuss about this. So in Fourier's law, you need to understand about the four concepts. First thing you need to know about the laws. So the law, you have just understood it. It's the rate of flow of heat is direct proportion to the cross-section area and the direct proportion to the temperature gradient. The second thing that you need to understand is about the U values. And the third thing you need to understand is about the thermal resistance. And the fourth one is about the thermal equivalent length. Are you there, Chief? Let's move here. So talking about the Fourier's law, I'm just going to say about the first thing I've just said. First thing is about the law. I've just stated it, the law. One thing. The second thing that you need to understand in order to say that you understand about the Fourier's law is about the U value. The problem is here. Students just know how to say the Fourier's law, but they don't know the criteria for question. I've just solved a lot of questions on this Fourier's law. Thousands of questions, but actually I've just come to recognize there are some basic concepts which I've now said you need to know how to state law. What are the terms in the law? Technical terms here, 3. But the other thing is about the U value. What's the U value? Why U value and not thermal conductivity? Because U value the same resembles to the thermal conductivity. So you need to know the difference and why the difference. The third thing that you need to know about the Fourier's law actually is about the thermal resistance. What is the thermal resistance? That like in electrical resistance, there is a thermal resistance because here is the conduction, Chief. If you have to move from one point to another, there is the opposition. What's the opposition in terms of thermal conduction? The fourth thing you need to know actually, Chief, you need to know about the thermal equivalent length. Are you there? Let's move on. So talking about the second thing that we need to know is about the U values. So talking about the U values, these we say U values is the same as the thermal conductivity. U value, as we said for the thermal conductivity, we said what the thermal conductivity? Listen here, thermal conductivity, which is now I've said is K. You just obtain it from here. You just say it's the heat, rate of heat flow, this one, you divide by area, you divide by the temperature gradient, you do the 1 over x. So actually talking about the thermal conductivity is the rate of flow of heat for a given area for a given temperature gradient. The same as U value, but U value is the rate of flow of heat for a given area of the conductor or the region, but for a given temperature difference, not the gradient. Why U value? The U value is more important because it just considers the difference in temperature and not the gradient. The moment you consider about the gradient, meaning you're considering about the length. So that is about only conduction. So the thermal conductivity only, K, only considers about conduction. But talking about the U value, only considers about the U value, considers about conduction. Because in conduction, there is a difference in temperature. And in radiation, there is a difference in temperature. Radiation from the hot object to the cold object, radiation. And what is convection? Convection. So they will ask you a question. Why engineers tend to use more U values than the K, the thermal conductivity? What's the reason behind? The U value is most used by engineers in construction to calculate the rates of flow of heat. It's because it considers the loss of heat or the gain of heat through the three methods, while the K value only considers for the conduction because we consider the gradient, while for U value we just consider the difference in temperature. Are you there? Dang. So talking about this, you have just understood why U value. You need to know why U value and not K. There is where, Chief, you need to understand. Okay, I said about the U value. What's the thermal resistance? The third concept that I need to understand, you need to understand in Fourier's law is about the thermal resistance. Thermal resistance. What is thermal resistance? So talking about the thermal resistance, this is just the opposition to the flow of heat. And we said, for example, let me use the relation. Let me use the relation. Look here. We said in current, what is current, man? We said the rate of flow of charges. Current is actually the rate of flow of charges. And what is it now? Is the potential difference between the 2 points over the resistance. That's where, Chief, you said, you said from Ohm's law here, current is just equal to V over R. So the same in the rate of flow of heat. We have the thermal resistance. So talking about the thermal resistance, actually, the rate of flow of heat, the heat flowing per time, Chief, is just equal to the temperature difference. So talking about the temperature difference, we just say the temperature difference over the thermal resistance. That's what we say. Talking about the thermal resistance now, RT will just be equal to what? The temperature difference over who? Over the rate of flow. Rate of flow of heat. Are my words visible? Let me see from my camera. Is that visible? Yes, it's visible, Chief. Let's move on now. So where is my duster? Okay. Let me lab here. Let's go. I'm just finishing about the Fourier's law. You need to effectively understand the concepts before you go anywhere. Because in learning process, I told you, if you haven't looked into my videos that I've just explained, how to start successfully physics. You have the 4 stages that you need to make. The 4 stages. And one of the stages, as I said, you need to have the clear understanding. And what criteria to have the clear understanding? You need to have a professional, not only a professional teacher. It's not about a professionality. No. It's about a mentor who can give you the exact concepts that will help you to solve the problems without even thinking about it. And that person is me. Not only me, but also there are some other teachers. But you need to choose exactly mentor who specifically know what is happening, what was happening, and what will happen before. Dang, go and watch that video. How to start to get an A. Let's go on. So talking about the thermal resistance, I've just talked about the thermal resistance. I've just talked about, and I have to conclude it. Thermal resistance is about the what? The temperature difference, temperature difference over who? Temperature difference over the rate of flow of heat. But we said from Fourier's law, what the rate of flow of heat? Rate of flow of heat is just Ka. We have the difference in temperatures, which is d theta over gradient. That's about the rate of flow of heat, the length. So that's the gradient. So if I substitute it here, I just say the temperature, but over who? Over the rate of flow of heat, which is the rate of flow of heat, Ka d theta over x. So this shift cancels with this. So talking about that, what do I mean? Meaning the thermal resistance now will just be, this is 1 over Ka over x. So this means it's just equal x to Ka. Okay, so kumbe the thermal resistance will just be x over Ka. That's all about the thermal resistance. That's all about the thermal resistance. Dang. Okay, let's talk about, that's about the thermal resistance. How if, Chief, I move to the thermal equivalent? Thermal equivalent. The fourth concept that you need to understand in conduction is about the thermal equivalent length. Take a consideration here. Come on. You know, conductors are good conductors. They tend to allow the passage of heat through them easily. So the rate of flow through the conductors is very high. How if you take the insulators? Meaning the rate of flow of heat through them is bad and it's small. Come now. If I take an insulator with this length and the conductor with this length, you see, you can find the rate are equal. Because these have very small length and it have the very bad or a small rate of flow of heat through it. While this one have very large rate of flow of heat because it's a conductor. So if I've just put the difference in temperature between here and here, the same as the temperature between here and here. And the cross-section area of this is the same as the cross-section area of this. Chief, that length of the conduct will be the thermal equivalent length to that of the insulator. So, come on, talk about the thermal equivalent length. It's the length of a conductor. Come on, it's the length of the conductor which have the same rate of flow of heat as the insulators, but the insulator should have the same temperature difference as that conductor and the cross-section area the same as that of the conductor. So if the length are equal, that length of the conductor is the thermal equivalent to that of the insulator. The length, they can't be equal. Actual lengths can't be equal, but the thermal equivalent length is, that's why we say equivalent, because this material has just conducted heat in the same rate as that one. So this means thermally, actually, they have the equal lengths, but they are not in actual. Why? It's because conductors, they have the large rate, while the insulators have the small rate. So you can just take a small conductor like this, my finger here, while you take the insulator like this one and the conductor like this one. So you have the same rates of conduction. Now the length of the conductor will be actually what we say the thermal equivalent length. So this is first thing you need to know is about the length of a conductor. Criteria is the condition should have the length of the conductor which providing the same rate of flow of heat flowing per time. But come on, come here. The condition should be same temperature gradient, and the cross-section area. Under those conditions, if I don't see those terms, 3 terms in your definition, you are wrong, chief. So summarizing this, if you have this is the conductor, and you have this is the insulator, you see, hey, let this be the insulators, while this should be a conductor here. Let's reduce the strength, because this length will be the thermal equivalent length to this one if they have the same rate. Rate here, let's just equal to this rate, because actually this conducts very slow. Takes time to think about that. Is that good now? I just move to the other concept, which is about, I've just talked about the Fourier's law. I'm just talking about the law, the U value. I'm just talking about the thermal resistance, and I've just talked about the thermal equivalent lengths. So I'm just going to move to the radial lines of heat flow. Let's talk about the radial lines of heat flow. Okay, let's discuss about this. Radial lines of. Talking actually, is microphone okay? Yes. So, chief, talking about the radial lines of heat flow. Here, you need to know about. So we're just going to finish about the conduction. Then up there, we are going for radiation and convection. Radial lines of heat flow has the 3 parts that you need to understand. There are many cases that can be described, but basically in these 3 will give you the view on how we do it. So the Fourier's law, actually, we consider for just a rod like this, having a certain cross-section and a certain length, and heat moves from this side to this side. How if inside is hot, and then that heat we need you to calculate is coming out? That's where we say the radial lines of heat flow. It's not linear, as we discussed previously. So even if, for example, I say, let me take an example. Oh, okay. Here, do you see this? If heat moves from here to here, chief, you do it as a Fourier's law. Be keen in solving this question, man. Look at me. So talking about actually solving these questions, you need to think about which case is the man talking. Listen to the question very carefully. So when it's just describing the heat moves from this side to the other side, you use the previous formula. But when describing the heat moves from inside to the outside through the thick cylinder, you just say this is like a cylinder. You just do what am I going to do here? If it's a sphere or it's a cycle, you just do what am I going to do here? So the radial lines of heat flow, which is not linear now. For example, heat moving from inside the earth, from the core to the outside. How do you do it? Let's go on. So talking about here, I just got to describe about, let me describe about actually things like conduction through a thick spherical shell. The second thing is about conduction through what we say a thick cylinder. And the third thing here, we need to say conduction through, let's say through an ice, or let me describe it as a freezing of the pond. Freezing of a pond. Freezing of a pond. Right. So let me discuss about these things. Let me discuss about these things actually. Let me start, for example, with the freezing of the pond. Freezing of the pond. Freezing of a pond. This one, the third one. So talking about the pond, actually, a pond is the masses of water just displayed in air. So if I speak the pond, I speak about water. So you need to know actually the properties of water in heat conduction. There is a certain property specifically called the anomalous behavior. I know you know it, but I need to tip something. Talking about the anomalous expansion of water, this is just now the property that is being displayed by water only that tends to deviate from the normal properties. We know the normal property of anything. When you heat it, meaning you are just making it to expand because you're increasing the kinetic energy of particles. So for water, when heated from 0 degrees centigrade to 4 degrees centigrade, it doesn't expand but tends to contract. What is density? The degree of compactness. So if something is contracting, meaning we are increasing the density. So the anomalous behavior, talking about the anomalous behavior of water, is the behavior of water when heated from 0 to 4 tends to increase its density or to decrease its volume, while normally we expect it to increase. Dang. So talking about the freezing of a pond, we need to know about anomalous first. Anomalous expansion of water. So talking about the anomalous expansion of water, what does it mean, man? Talking about the anomalous expansion of water, this means actually the increase in density as being heated from 0 degrees centigrade to 4 degrees centigrade. And let me show you here. So when defining it, you just say is the increase. For example, the density, let's say, is 0.9999. It just tends to increase. Actual density is just 1.8. Let's say 111 or 0001, something like. So it just tends to increase its density. The density of water approximately is equal to 0. So the change is very small, but it can affect some experiments. So we just say if it increases to the maximum density here from 0 degrees centigrade, if this is the temperature axis and this is the density axis, density. So the density tends to, this is in gram per centimeter cubic, but if you talk about the kilogram, you just put 100, so 1,000. So here, from here to a 4 degrees centigrade, says that its density to increase, meaning if you draw in terms of volume, this is the volume and this is the temperature. So meaning the volume tends to decrease instead of increasing from 0 to a certain here to 4 degrees centigrade. So the volume tends, if the volume was this one, tends to decrease to somewhere else, and then tends to increase. So the volume tends to decrease first before in expansion, in heating from 0 to 4 degrees centigrade, and then it starts to decrease because as you heat, it's just decrease the density. Yeah. Let's go on. So the anomalous expansion of water actually is what we say that the that's why we say anomalous, abnormal behavior. But the normality we need to. Okay. So freezing of the pond here, you need to understand about the assumptions that we made in calculating these questions of freezing of the pond. There are 4 assumptions that we made in calculating. So you can just be given a question, by how much time the ice will just reach a certain kilogram or a certain length. So when you are calculating that value, finally they ask you, hey, can you give us some 2 assumptions that you made when calculating that? So you need to be keen in these questions. It's not about understanding only the concepts. You need to understand the right concepts here. Basing on your questions, you need to know about the assumptions that we made in calculating this freezing of the pond. Look here, we say if this, let me show you, if this is the pond now, meaning there is water, chief, there is water here. Due to anomalous expansion of water, there are some organisms survives here, to live here inside during the cold conditions, because during the cold condition, chief, air flows upward. So as air flows, air is too cold, chief, during the cold condition. So makes water here to turn into ice, inducing the coldness on it. So this is the ice formed due to the flow of air. So, but here, as it's being cooled from here, 0 new centigrade, here, just below it, the ice, as being cooled to here is hot, 4 new centigrade. So organisms tend to survive in this zone. But what you need to know, they will ask you some questions like, by how much time the length of the ice will just be something. So let's say the thickness of that ice is X. And the first assumption that we assumed that just below the ice, the temperature is 0 new centigrade. The second thing is about the temperature here above. We assume it's a negative temperature. That's the second assumption. The third assumption, we assume that ice conducts by conduction. It conducts heat by conduction. It transfers heat by conduction, not by radiation, not by convection. So ice, we assume, is a conductor of heat. So first thing I've just said, conduction, ice, transfer by conduction. The second thing I've just assumed is the temperature below is negative. Is 0 new centigrade. This is below, just below the ice. While the third thing is about the temperature is negative. Is negative theta new centigrade, just above the ice. Above ice. That's all about. Hey, let's do this. Now for the calculation, mathematical calculations. Let's do this. So in mathematical calculations, how do we develop the formulas for calculation of such a case? We just say, if it conducts heat by convection, oh, dang. If we conduct heat from here to here, meaning here is 0, here is negative. This means heat flows from here to here, meaning from 4 to 0 to negative, because always flow from hot to the cold junction. So talking about that, we just say the heat flowing per time is just equal to K but to A with the who? What is it, man? It's about the temperature, which is 0 minus the negative theta. That's all. But the through X, yeah. So what is it? We say heat now flowing per time is just equal to K A theta over who? Over X. That takes as equation 1. Second thing that you need to know, that's water. So if it's water, meaning, and it tends to form an ice, you learned about the latent heat. So if we had a liquid turning to be ice, that's latent heat of fusion. So getting the heat that has changing so as to make it to turn to ice, we can get it. The heat is just equal to M with the latent heat of fusion. You remember about that, Chief? Yeah. So talking about the let now, in order to make the comparison with this, we divide by time. So having the rate of flow of heat using this formula will just be equal to the mass latent heat of fusion, but over time. You see now? So we can make comparison because this is equation 2 is the same as equation 1. So being equation 2 the same as equation 1, we can make now comparison. Let's make comparison. Let's make comparison now, Chief. Let's make comparison. Let's make comparison. Let's make comparison here, Chief. We can now say MLF. That's all about over time. That's all about this equation, which is Ka, who is theta over who? Over x. That good, Chief? Yeah. But you need to know actually here. Look here. What do you need to know? This is the rate of losing heat from water to some layers to ice, then outside to the environment. Yeah. So here the rate of losing, we put the negative. The rate of losing, we put the negative. But the rate of gaining, you see, it's not losing. So we just say here we have the negative here because we are losing heat. So talking about this, Chief, look here, we can say what is mass? Mass is just equal to density times the change in volume. What's the volume now? If we have this ice, such like that, let's have the area. You see, but times its length, we can now get the volume for that ice. So the volume is x, the change dx, but who? With area to get the volume. Oh, so when we put it here, we just say density A dx over time, a dt, a change in time for a given change in length. We just have the LF, which is just equal to Ka with theta over who? Over x. So here from there, you can just be asked the three type of questions. One, they will ask you about the rate of formation, of ice. How much ice is being formed by how much time? That's the rate. The rate of increase of ice or decrease of ice. So, but here we are just talking about the increase of ice because we're just talking about that negative, the loss. As the temperature is being lost, water is more turned to be ice. The second thing is actually we're talking about. They will ask you what is the increase in ice if they give you the initial time to the final time that they want. So the increased ice, increase the thickness. And finally, they ask you the final length, final or initial length, How do you get these questions? Get me clear here. Three questions that can be asked. The first thing is about the formation of ice. Let's discuss about the formation of ice. Formation of ice. Hey, Chief. So talking about the formation of ice here, we say the rate of formation of ice. This is now dx over dt because our ice, do you remember it? Our ice was like this. So it's the length that is being formed over time. A change in time is what we call the rate. So if they ask you about the rate of formation of ice, this means how much ice has been formed for a given time. So this is about the dx, length of the ice, dt, but over, so area and area cancels. Here we have only k, we have the theta over who, we have the x, we have latitude of fusion, and we have what? We say the density. That's all about. That's how we get Chief. So you just make the subject. The other thing that they will ask you about the thickness increased. Just the dx, thickness increased. If they ask you about the thickness, that is dx, thickness increased. inclusivity. So it's the change between the final and the initial at that initial time that they considered the formation starts. So the dx, thickness inclusivity. So it's dx. How do you get it, Chief? This means times there. So you just multiply k theta over density LF, then x, and then what? dt. There is where we go, Chief. How about now let's talk about things like the final and the initial length. Now, there is where comes a problem. Come here. See, what am I talking about? Don't worry, PCBs, if you haven't started about integration, leave this room, go and start about the integration. But I will teach you some simple formulas. But make sure, studying physics, you need to know about differentiation, integration, trigonometric ratio. Before you start any topic, just go and start about that. If you haven't studied it, find a Form 6 to help you. Then you come back to class. Let's go on. So talking about this, we say, now talking about the initial and the final length is, we say, from there, the dx is just equal to, let's correct the like terms, x, before integration. So we say k theta over density latitude of fusion, and what we say, this is dt. So actually talking about the final and the initial, we just integrate this from when x it was initial, let's say 0, and when it was at time t, given time, and when this was 0 to given time t. So we can just obtain q theta over we say this is density latitude of fusion, and what we say, this is t. While we talk about this is when you integrate. Now look here, those who don't know integration, when you integrate something in this form, xn dx, you can just get xn plus 1 over n plus 1, Chief. So here we just have 1 to our x. So we have what? This will just be x. 1 plus 1 is 2 over 2, because here we just have 1. So the n is just 1. So from x naught to x at that time, that's equal. So talking about this, you put it inside, you minus this. So this is xt square over 2 minus xc naught square over 2. That's all about, Chief. So you just have k theta over density latitude of fusion times what? Time. So talking actually about this, the thickness made, either initial, you make the subjective, or final. Final, you make this. Initial, you make this. So for example, let me make for the final. For the final, I can just say this comes to that side. So we just multiply density LF multiplying by time, but plus x naught square over 2, Chief. So you put the square root. That's all about the length at that time thing. There we go. So moving from there, that's all about what we can say. It's about what we say, the conduction. That's all about we say about the conduction. Oh, freezing of the pond. I haven't finished about the through the thick spherical shell and through the cylinder. What's the time? Let me look at the time. Okay, 1 hour. Still is good. Let's move on. Let's move on for the through a pond. Let's finish for the pond. We have just done for the pond, and actually that's the formula. So let's go for these two to finish. Our time is up. Time is up. Let me do fast as possible. Let me do fast as possible. Okay, so let's go on. The second concept that I said is about the conduction through a thick spherical shell. Let's discuss about the thick spherical shell. About the conduction through thick spherical shell. Thick spherical shell. So when talking about the thick spherical shell is about, let's see here, example of a thick spherical shell. A spherical shell here, spherical shell like this, spherical shell like that, spherical shell like that. This is spherical. So if it's spherical shell like that, this is not visible. Okay, that's good. It's visible now. So let's say if this is shell, the inner, now the inside here is hot. Let's say at temperature 1, while the outside is temperature 2. So heat flows always from the hot region here to the cold region outside. So for example, here inside is hot flowing to come outside, not from the hot to the out to the cold through linear. But so talking about this, if this is the radius for this, from here to here, this is R1, and from here to here, this is R2. So there is a difference in radius between this radius and this radius, which is now the dr. Let's consider the change in length, I mean in radius, which is the difference now between this radi and this radi. If you minus it, you get this, the dr. So talking about the rate of flow of heat, will just be equal to heat per time, which is K area, but the temperature difference, which is theta, the temperature, we put it here, the temperature difference, so the change in temperature between this and this, the hot, over a given length, which is what the changes is dr there. However, from who? From the Fourier's law. Fourier's law. You see? So what's the area for the sphere? Area for the sphere is 4 pi r square. Yeah. So when we put it here is 4 pi r square. But times who? Times the d theta over dr. That's what we say the change for heat per time, the rate of flow of heat. Is that good, Chief? That's good. Let's correct the like terms and integrate that. So talking about that, we can just say, hey, for this sphere now, we can just say, how about that? We can just say rate of flow of heat flowing per time. Let's collect the dr there, the radiuses of r, because we are integrating the radiuses and as the temperature increases to the cold junction. It's just equal to, this is square, so let's put the square here. This is d theta, we just have the 4 pi, the 4 pi k, and what? And d theta, yeah, d theta like that. Good. So if we integrate from who? From actually, you need to remember, if we have the loss, this is negative. If we forget about that, we can get the good results. So we put the negative. If we integrate now from R1 inside to R2 outside, and here we integrate from temperature 1 inside to temperature 2 outside. So what are we going to get? The rate of flow of heat now per time is just equal to, who is this? This is when you integrate it. I told you PCB. Look here. We said actually when you integrate xn, the x is just equal to who? Xn plus 1 over n plus 1. So here we have 2. We have a negative 2. If you correct this one, you just get, because we have the dr over r square, so you just get negative 2 dr. So here, Chief, is r negative 2 plus 1 over negative 2 plus 1. So that means we just have r negative 1 over negative 1. That means negative 1 of r. Is that clear, Chief? Yes. So let me wrap this. This is not physics. This is about mathematics. You need to know about the integration. So we have here what is called the 1 over r negative. So moving from where? From r1 to r2, Chief. Is that good? Yeah. So from there, let's just say is 4 pi k from theta 1 to theta 2. If you integrate the x, it's just equal to x. So the theta will just be equal to theta. theta. So, but from where? From theta 1 to where? To theta 2. And then you minus the factors as the inter inside. So just say rate of heat here is just equal to, who is negative 1 over R2. Then I minus the negative 1 over as R1. So it's just equal to 4 pi k, who is, but here there is a negative, chief, theta 2 minus theta 1. That's good. So if I minus this, this is plus. So meaning if you find the KDS is about theta, this R2, R1. This is R1 minus R2, isn't it? So because this is negative, so this means if I divide by R1 here, this means I divide by R1, I just get R2. If I divide here, it's just minus R1. Are you there? Yeah. So I just get, what is it, chief? This is dH over dt, which is now equal to, what is this? This negative enters inside. This means is 4 pi k. Then what is theta 1 minus theta 2? That's all about, chief. So talking about actually the rate of heat through a spherical shell now will just be the rate dH over dt will just be equal to, now you make the subject is R1 R2 4 k pi, then who, theta 1 minus theta 2 over who, R2 minus R1. Is that clear, chief? Not this. If you forgot about everything, don't forget that what you minus is not it's not the smallest value. For example, for the radius, the smallest value is R1. You don't minus R1 minus R2. And if you don't put that negative, that there is a decrease in temperature here initially, you just get the reverse of the formula. So you got the incorrect answers. But to get these positive values, actually the rate of heat, you need to take this largest radius minus the smallest radius, and the temperature, the largest temperature will be the inside as it flows to the cold junction, which is theta 2. So you take the theta 1 minus theta 2. If you get that in your formula, in your derivation, you are correct. If you get the reverse, meaning you forgotten about the negative. Let's go on. So we said about that. So that's about the spherical shell. How about a thick cylinder outside? Thick cylinder outside. Let's discuss about the thick cylinder outside. Let's discuss about the thick cylinder outside. Thick cylinder outside. Let's discuss about the thick cylinder outside. Okay. So talking about the thick cylinder outside, thick cylinder. Conduction through a thick cylinder. If we have, this is our cylinder here, cylinder like that, and have a certain length L. But we know inside is hot. It's hot, chief. Inside is hot. So we have the temperature theta 1 here inside, and we have a certain that. Oh, let me draw it in large. Let me draw it as a larger object to be visible to your camera. Kamala, a president of America next election. Kamala. Okay, so let's say about this is the hot temperature theta 1, while its radius inside is R1. So the radius outside is R2, and here we have the temperature 2 outside. Chief, look here. This is the R, the difference in radiuses. And it's have the length L here. Length L. Chief, this is the length L. So talking about the heat, the rate of flow of heat is actually K area, the temperature gradient, the dr. So what about A? Area for this is just equal to pi r square, then 2 pi r. 2 pi r L, meaning the perimeter for this and times its length. That's about the area now. The 2 pi r for the cycle, the perimeter, then times the length. So this means if I put here, it's just equal to K, then it's 2 pi r L, then d theta over dr. So talking about that, we say the rate of flow of heat, the flowing per time, is just equal to dr over who? Over r. Then it's just equal to 2 pi k, what? L, 2 pi k L, and we have the d theta. So this r, we have just corrected them. R with dr, we have just corrected them. So this means if I speak to integrate this, I integrate this temperature from theta where? From theta 0. Oh, we haven't put the negative. Don't forget about that, man. So we put the negative here to show there is a decrease. There is a decrease. So we say if you integrate from R1, R2, the same thing as we did. When you are just given the radial flow, you just do the same thing regardless of the shape. What you consider is the area. So there's the go here from theta 1 to the final theta 2. So let's talk about dH. The dH flowing per time is a what? Chief, if you integrate these PCBs, do you remember that formula? If you integrate xn dx, what do you get? So we have here r negative 1, because if this rises, the r negative 1, the r. So that is, we plus 1, we minus 1. This only works if n is not equal to negative 1. If it's negative 1, you just put this integration of xn dx. If its n is also 1, it's just equal to ln of x. Ln, the natural logarithm for x. So this doesn't work for negative 1 because when you put 1, it will just be 0 over 0, undefined. Okay, let's go on here. So if we put this, meaning if I put this actually here, will just be the ln of who? Of r. There's a principle. You need to learn about integration before you go anywhere. So R1, that's R2, and just equal to who? Negative 2 pi k L, and what? This is theta 2 minus theta 1. So talking about this is dH over dt. It's just equal to, this is before you make the subject here, you say ln of who? R2 minus ln of R1. You get me correctly? Yeah. So that is about negative. If it enters this is 2 pi k L, and negative will just be theta 1 minus theta 2 instead of theta 2 minus, because of this negative. So talking actually about the dH now, which is lead, which is what we want, chief. Just drive, what we want is the final formula. So as I may claim, no, never claim about this. Just repeat it. Just repeat it and understand about what I'm speaking about. So talking about this is actually equal to 2 pi k. Am I mark a pens over? No, you can't do that for me. Let me look for the other. Oh, okay. So this is dH over dt, 2 pi k L. We have theta 1 minus theta 2 over who? This is ln. If you minus the ln, first the natural, it's the natural logarithm for the logarithmic rows that you started in O-level. So if we minus, that means we divide over R1. Chief, this is the formula to find the rate of flow throughout the ductile. Okay, that's about the conduction. How about the convection and radiation? See you in the next video. Dang, it has the 4 videos. This is the second video just for only conduction. Then the first was thermometry, the second is for conduction, the third will just be about convection and radiation, and the fourth one will be about the thermodynamics. So let's go, subscribe, invite your friends, and let's do together. Let's go and get an A, and when you get it back an A, make sure you inform us so as our statistics may be observable for the future world. Clap for me, Chief. It's Kusekwa signing out, man.